So let's talk about how temperature affects the solubility of gases in liquids. So if you recall, what we said about solubility of solids in liquids was that if the dissolution process on the whole is endothermic, meaning it's absorbing energy, then increasing the temperature is going to further the dissolution process, meaning you can dissolve more solute in that solvent at a higher temperature. And then on the other hand, if the dissolution process is on the whole exothermic, then increasing the temperature is going to reduce the solubility. So the similar logic applies to solubility of gases and liquids as well. So again, we have to look at three types of interactions here: the solute-solute interactions, solute-solute interactions. Then you have solvent-solvent interactions, solvent-solvent interactions, and then you have solute-solvent interactions. So in case of gases dissolving in liquids, as you can imagine, the only interactions between gas molecules are pretty weak because they are bound together only by these weak van der Waals forces. So you practically require close to zero amount of energy to break or to disrupt these interactions. So that part that was highly endothermic in cases like ionic solvents, solids dissolving in water, for example, we looked at sodium chloride and we said the amount of energy required to break the network, break the ionic bond network is really high. So that was a big endothermic step in those cases. So in this case, so as I said, this step doesn't take any energy at all. So again, when you come to solvent-solvent interactions, so we said in solvents like water, for example, the water molecules are bound together by hydrogen bonds. Again, these bonds are not very strong, so it doesn't require that much of energy to break these bonds to accommodate the gas molecules. So this is an endothermic step, although the energy required is not that much. So then you come to the solute-solvent interaction. So again, if you have polar gases, for example, like ammonia, so that is readily soluble in water, So you can imagine in this case, this step is exothermic. It releases energy if it is a polar molecule dissolving in a polar solvent. So what we have here is dipole-dipole interactions, and we already talked about this. And so these interactions are what release energy when ammonia dissolves in water, and this is what makes the entire dissolution process exothermic. So that is pretty clear. So what happens in case of non-polar molecules, non-polar gases, like for example oxygen, nitrogen, CH4, methane, when these gases dissolve in water? We know that these are sparingly soluble in water. We already talked about that. So what is it that actually allows them to dissolve in water, even if it is, to a very small extent? So the interactions, the solute-solvent interactions in this case are what we call dipole-induced dipole interactions. Dipole-induced dipole interaction. So what these are is basically when a non-polar molecule comes in a close proximity to a polar molecule. So let's say we take the example of oxygen, and there are two oxygen atoms that share two pairs of electrons, and they are evenly distributed between the two atoms, because there's no reason why these electrons should move closer to one oxygen atom than the other. But what happens when it comes in close proximity to a polar molecule, like for example water, and we know that this is clearly a dipole. It has a slight negative charge on the oxygen and then slight positive charges on the hydrogen atoms. So when the negative side of this dipole comes close to this non-polar molecule, it tends to repel these evenly distributed electrons. So this sort of distorts the electron density here. And then similarly, if you have the positive side of the dipole coming close to the non-polar molecule, it's going to attract those evenly distributed electrons. So in either cases, it's sort of introducing this temporary dipole in this otherwise non-polar molecule. So So again, these dipoles are very temporary, and these attractions die down, and then this molecule returns to its normal, state. But so as long as this dipole remains, this interaction here is exothermic. So that is releasing energy. So the dipole-induced dipole interactions are very weak, as you can imagine, compared to the dipole-dipole interactions. Here the dipoles are permanent dipoles, as we know, and these interactions are comparatively, relatively much stronger than these temporarily induced dipole-dipole interactions. In any case, what we observe in most gases dissolving in solvents like water is that the overall dissolution process is exothermic. So it actually releases some amount of energy depending upon what kind of a gas it is, whether non-polar, polar. It's going to its solubility is going to be different in polar solvents like water. But in general, if you notice gases dissolving in water, they release energy, and this process is exothermic. But don't get me wrong, there are examples of systems, of solute solvent systems, where the gaseous solute dissolves in the solvent, with the overall dissolution process being endothermic. So we already know by Le Chatelier principle that if a dissolution process is exothermic, increasing the temperature is going to decrease the solubility. So for example, this can very well be seen in dissolved oxygen in our water bodies like rivers and seas and oceans. So what happens is the aquatic life in these water bodies are going to be very much dependent on the dissolved oxygen, as we all know. I mean, they get their life supply of oxygen from this really small amount of dissolved oxygen in water. So now one big concern in case of setting up industries on the banks of these rivers is many times these industrial plants use water as a circulant or as a liquid to basically act as a heat sink in all their processes. So once they're done with the circulation, they basically dump that hot water into the nearby rivers or lakes. So in that case, the temperature of these rivers and lakes goes up, and the dissolved oxygen levels go down as a result, and then the aquatic life actually suffers quite a bit because of that. So that is a trend people have observed, and it is of a great concern to environmentalists. And if you so by the same token, if you reduce the temperature, that is in cold climatic conditions, there is increase in solubility of these gases by Le Chatelier's principle. So if you were to look at this whole process atomistically, just to give you some intuition here, let's say you have a system where you have these solvent molecules, let's say they are water molecules. In this gas phase, these have a certain average kinetic energy, and these gas molecules are moving in all directions, and they're colliding with one another, and some of them actually make their way into the liquid phase, and once they are inside, they basically get trapped by these cage of these liquid molecules, and there is sort of a dynamic equilibrium between the number of gas molecules entering the liquid phase and the gas molecules exiting the liquid phase. So at any point, some of these gas molecules will have enough energy to basically break away from this cage and get out of into the gaseous, back into the gaseous phase. So there is this dynamic equilibrium here. So now what happens when you increase the temperature? So the average kinetic energy of this whole system here, of the solution here, goes up. So the number of gas molecules that can actually break away from this cage and get back into the gaseous phase is also more. So that's why the new dynamic equilibrium that gets established at a higher temperature is going to give rise to a lower solubility of this gas in the liquid phase. So that is another way to think about it. When you increase the temperature, why the solubility goes down.